Okay, let us start off with the AXI interview. So, yeah, what is the
Mm-hmm.
difference between AXI protocol and what are the differences between AXI and compared to HB and APB?
AXI, or Advanced Extensible Interface, is the most feature-rich. Let me compare it properly to AHB and APB. Though in an interview tone, AXI supports burst transfers, separate address and data phases, multiple outstanding transactions, and separate read-write channels, so it's high performance and pipeline. AHB is simpler with a single shared bus, supports bursts, but only a single outstanding transfer at a time, so it's less pipelined. APB is the simplest, used for low bandwidth peripheral registers, no bursts, no pipelining, and straightforward read-write access. In short, AXI for high performance designs, AHB for medium complexity systems, and APB for simple peripheral access.
Okay, can you give
And
an
that's what
example? Yeah.
employers usually want to hear. Sure, for instance, a CPU talking to external memory, like DDR, typically uses AXI. An internal peripheral bus bridge often uses APB for simple register reads or writes, and AHB might be used for mid-speed peripherals such as DMA controllers or SRAM bridges. If they ask why AXI is faster, say independent channels plus IDs allow more overlap. That usually lands well. Do you want me to go into handshake signals next?
Okay, yeah, this can you tabulate all these differences? Can you hear me? Can you tabulate all these
I can, yeah.
differences? Hello, can you
Looking
tabulate
that
all these
up,
differences? Yeah.
just say. Sure. Here's a clean comparison. AXI, high performance, multiple outstanding transactions, separate read-write channels, burst transfers. AHB, medium performance, single outstanding transfer, shared bus, burst support. APB, low performance, no pipelining, no bursts, mainly for simple peripherals. AXI supports transaction IDs and out-of-order completion. AHB and APB do not. AXI burst length can go up to 256 beats. Let me just check something real quick. Thanks for waiting. Here's the table. AXI, high performance IDs, out of order completion, separate read-write channels. AHB, medium single bus, burst single outstanding. APB, low speed, simple peripheral bus, single transfers, no pipelining. AXI uses valid, ready handshakes. AHB uses H-ready, H-press-up. APB uses PISO, pinnable, pretty. Arbitration needed for AXI interconnect, not typically for APB. So you can emphasize performance scaling and complexity differences in interviews.
Okay, give an example or illustration with a real case scenario, a real case system where you might have different protocols and what will be your choice of protocols and where do you use them.
Checking that. A good interview example is a smartphone SoC. CPU to DDR controller uses AXI for high bandwidth. Mid-speed IP like Ethernet or SRAM uses AHB. Then AHB to APB bridges to peripherals. Low-speed blocks like UART, I2C, timers use APB. Explain AXI by saying the CPU moves lots of data to XHB, needing high bandwidth bursts, while UART's configuration registers don't. So AXI for the data path, AHB for mid-speed bridges, and APB for low-speed control peripherals to save area and power.
Okay, so what happens if we use AXI protocol for all the cases?
If you use AXI for everything, it works, but it's overkill for simple peripherals. It'll increase logic complexity, area, power, draw, and verification effort. So the common practice is to reserve AXI for high throughput paths, use AHB where moderate performance is enough, and APB for low power control registers. It's about balancing performance versus cost.
Okay, what happens if we use HP or APB for all the paths?
If you use AHB everywhere, it'll function but bottleneck high speed transfers, and peripherals will be unnecessarily complex. Using APB for everything will severely limit throughput, not suitable for CPU or memory. So match the protocol to the bandwidth and complexity needs.
Okay, can you take a real case scenario or example with data and explain how the HP protocol or APB protocol will fail in case of a CPU to DDR path?
Checking that. Yes, that's a classic interview angle. Say a CPU at 1 gigahertz with a 128-bit DDR interface. With AXI, the CPU can issue multiple outstanding transactions and keep the bus busy, maximizing memory throughput. With AHB, only one transfer can be outstanding, so the CPU stalls during DDR latency, underutilizing the bus. With APB, it's much worse. No bursts, no pipelining. Each word transfer is sequential, so performance tank. That's why AXI exists, to hide memory latency and keep bandwidth close to the theoretical max.
Okay, just can you make this illustration much more comprehensive? Can you tell me what is the data or the bandwidth throughput in case of all the three protocols and how will it differ in case of the three?
Checking that. Yes, a more quantitative angle does help. The bandwidth isn't fixed, but effective throughput varies with utilization. For a 1 gigahertz CPU with 128-bit bus, AXI with multi-outstanding transactions can keep the bus 90 to 95% busy, reaching about 14 to 15 BB cents effective. AHB with only one outstanding transaction stalls during memory latency, dropping to roughly 6 to 9 gigabyte cents effective. APB, being non-pipelined and sequential, is unsuitable for DDR traffic and would bottleneck badly. So for CPU to DDR, choose AXI.
Okay, okay, fine. And so in case of HCI protocol, so
Uh-huh.
what are the different types of bursts?
Checking. Okay, in AXI, there are three burst types: fixed, ing, and rep. Fixed keeps the same address each beat, good for FIFOs or registers. Ing increases the address each beat, the most common for memory transfers. Wrap increments, then wraps back at a boundary used for cache line accesses. Interviewers often ask how wrap boundaries are calculated, so be ready for that. AF, and if they press further, mention how burst length and transfer size interact with address alignment.
Okay, so can you explain how fixed address is used for FIFOs and registers?
Checking. Sure. Fixed burst keeps the same address every beat. So imagine writing to a FIFO data register. You send, say, 4 bytes. but the address stays 0x4000 for each beat. The device interprets each write sequentially. Same address, repeated transfers. That's how FIFOs or simple control registers are written using AXI. The address doesn't increment, only the data payload changes. It's simple and efficient for sequential peripheral access.
Okay, but if the address does not increment, then how is so the data will be keep returned to the same location, right?
Mm-hmm. Right. The address stays the same on the bus, but the FIFO hardware uses internal read and write pointers. So even though AXI always targets 0x4000, each write advances the device's internal pointer or register state. Same address, different data sequentially consumed by the device. That's why fixed burst is appropriate for FIFOs or single control registers. If you used ink bursts instead, you'd generate different addresses that might not map to valid registers. So for FIFOs and control registers, fixed address is the correct choice.
Okay. So, and where do we use the wrap burst?
Checking. Wrap bursts are used for cache line accesses. They're less common than ink bursts, but important in processor cache systems. For example, a 16-byte cache line with wrap fetches sequential addresses within the same aligned block, wrapping at the boundary, which fits how cache lines are laid out. That preserves locality and avoids crossing unrelated boundaries. So it's mainly about keeping cache line accesses contiguous and efficient. If you used ink instead, you'd cross into the next cache line, which isn't ideal for a cache fill. So wrap is the right choice when you must stay within a fixed cache line boundary. Imagine the CPU requests a word in the middle of a cache line. A wrap burst starts at that address and wraps within the same cache line boundary. This helps reduce latency for the requested word. So, in interviews, say wrap bursts are mainly for cache line fills and keep accesses inside the cache line boundary, avoiding crossing into the next line. And if they ask how to calculate the wrap boundary, that's the next common follow-up, worth practicing.
Okay, can you illustrate the scenario or whatever you mentioned about cache in a real
Mhm.
SOC or any kind of chip? What is the transaction? Who initiates it, and what exactly happens in the cache?
Checking that. Yeah. Here's a practical SOC scenario. Interviewers like. The CPU misses in L1, checks L2, then sends an AXI read to the DDR controller. CPU requests a 64-byte cache line. AXI bursts the request. DDR returns the line, cache fills, and the CPU resumes from cache. The cache controller, not the CPU core, initiates the AXI transaction and may use a wrap burst to keep within the cache line boundary. DDR returns data beats one at a time, and the cache updates L1. After that, hits within that line become cache hits. Using wrap keeps transfers inside that aligned cache line boundary, avoiding waste and improving effective bandwidth.
Okay. So can you map all these bursts to the ASP and the APP protocol and CHI protocols? What is the equivalent bursts we have in those protocols?
Checking that. Okay, that's a strong interview question. Here's how to map it. AXI supports fixed, ink, and wrap bursts. AHB supports single, ink, and wrap variants, but is less feature-rich than AXI. APB doesn't support bursts, only single transfers. CHI doesn't use AXI-style burst types. It moves whole cache lines via coherent transactions like read shared or read unique. So instead of juggling burst types, KHI bakes cache line transfers into the protocol itself. And that's the clean way to contrast them.
Okay. So can you explain more on how the CHI differs?
Checking. Yes, this is a common interview question. AXI is a memory mapped transaction protocol. CHI is cache coherent, uses requests, home nodes, and snoop nodes to keep caches in sync. AXI fits CPU to memory paths. CHI fits multi-core coherency directly. For example, if Core 1 reads data modified by Core 0, THI can automatically issue a snoop, fetch the latest cache line from the owning core, and keep everything coherent. Nodes you'll hear about include requester, home, and snoop. This reduces unnecessary DDR traffic and keeps caches consistent across cores. That's the big difference right there. And interviewers love it when you explain how coherent transactions prevent stale data problems.
Okay, so where do we go for XA protocol and where do we go for CHI protocol?
Checking? Let me just see. Okay, good interview framing. Say, XE is used inside subsystems for high bandwidth paths, like CPU to DDR or DMA to peripherals. Chai is the coherent interconnect for multi-core SoCs where CPUs, GPUs, and accelerators keep caches in sync. XE moves data efficiently. Chai keeps everyone seeing the same data version. That's the essence of the difference. And interviewers love when you show where each fits in a real smartphone SoC. AXI for high performance IP blocks, API for low speed peripherals. Don't use Chai for simple peripherals where AXI is more appropriate.
Okay. So
Mhm.
what do we mean by narrow transfer in XA protocol?
Checking? Yes, that's a common RTL question. A narrow transfer in AXI means transferring less than the full bus width. For example, a 64-bit bus transferring only 32 bits, the master sends just that portion, leaving the rest unused for that beat. Think of it as not wasting bandwidth by forcing a full width transfer when the data is smaller. So the byte strobes indicate exactly which byte lanes carry valid data. You use narrow transfers when the bus is wider than the data you need, like a 32-bit CPU talking on a 64-bit AXI interconnect. It's more efficient and avoids unnecessary data movement.